Hello everyone and welcome to Power Synergy. First, I want to express my special thanks to my first subscriber who motivates me to publish some videos. In today's video, I explore the complications of the single-diode model, a foundational mathematical framework that illustrates solar cell behavior. The electrical model of solar cells will be demystified and explained, and it will be broken down into key electrical parameters like photogeneration current, diode current, series resistant, and shunt resistant. Our visual exploration includes circuit diagrams and explanations, providing you with a deeper understanding of how solar cells convert light into electricity. Whether you are a solar energy enthusiast, researcher, or someone eager to harness the power of the sun, join Power Synergy on this informative journey to discuss the science behind photovoltaic systems together. Stay tuned for more exciting content on solar energy and sustainable technologies.
So first we need to import NumPy, and let's consider it as NP. And then we need to import mathplot library .pyplot. Let's have it as PLT. Then we define PV right, let's say model, and we have to consider voltage here. What other parameters? We have the current, radiance, temperature as Kelvin, and saturation current and phase current. The series resistance and shunt resistance. And good. The thing is, here voltage is the volt, current is amperes. For the radiance, as we show with G, we can say it watt over meter square. For the temperature, we consider it as Kelvin. And for the I saturation or I phase, these are in ampere, and for the resistance we have them in ohm. First, let's define our constants. As I explained in the equations, we have Boltzmann constant, which is K equals to 1.3806485 e to the power of minus 23. And for the elementary charge that we show it with Q, we have 1.6 0.21 You can find it is at the internet. It is available everywhere. The power of 19. Now it's time to thermal voltage, and which you can say that VT equals K multiplied by the temperature over Q. And according to the equations that I explained in the previous part, we can say that for calculating diode current, I equals to I saturation, that we have it, multiply by the numpy dot exponential of Q multiplied by voltage over and another parenthesis here, RS multiplied by VT that we had defined it previously. Now we are going to add the voltage as it's written here, minus IPH multiplied by RS shunt, and all of them are divided by R shunt. Now let's calculate the power, which all of us are familiar with it. It's equals to voltage multiplied by current. At the end, we are going to return the parameter power to our function.
Now it's time to run an example and see how can we use this code. First, let's make a voltage array and with numpy linspace it ranges from 0 to 1 with 100 points. So we create an array of voltages here. Then what we need to do, we should define the solar radiance, which is set to 1000 in this case. And the other factor that we should write is the temperature, which is in Kelvin. So we are going to write it 298. And the other parameter is I saturation. And I saturation is reverse saturation current, which is in ampere, and it is 1 multiplied 10 to the power of minus 12. And we have the I photon 5e minus 3, we can write it is the photocurrent that is in ampere, and the resistance, the series resistance, which is 0.1 ohm. And after this one we have the shunt resistance, which is set as 100. After setting all these parameters, it's time to recall our function, our PV model function that has been written in the previous part. So let's write power output and then recall our PV model function here. Be careful to set all these parameters in order to not to confuse, to not to miscalculate. So the first one is voltage array, and the second one we make it as none, and then we have the temperature, I saturation, I photon resistance, and shunt. We should add all of them to our function. Then it's time to plot our variables, voltage array and power output, and to see what the result is according to the equations that has been explained in the previous video and according to the function that is written in this Python programming code. Let's write the title and other things.
can name it as solar cell power model, and then labeling the X and Y axis. Our X axis is the voltage and the Y axis is the power. Here is the whole code that you can see. Now it's time to run the code. Let's see what the result is. Okay, there we have the plot. As you can see, with the increment of the voltage, our power increases, and that is the internal voltage in our solar cell. For different irradiance, we can have, let's say, different quantities. For example, instead of 1000, we can have it with 500, 1000 and 1500. Let's see how it differs with different irradiance, and the power and voltage, how do they differ. Be careful to modify the plot as well. And let's run the system. Here we are, you can see under different irradiance, under different conditions, we get different plot for our voltage and power. I hope you enjoy it and it will be useful for you.